Okay, here's the setup for the quantum magazine COP over 17 claimed circuit. This is the single MOSFET circuit implemented on the shifting paradigms board from SWIR, and I'm generating the timing from the DP101 pulse generator, and it is set to produce, this is the current pulse from the 0.25 ohm current viewing resistor. On this scope we have the raw gate pulse directly from the DP101, 12 volts, and this is displayed at 0.2 of a millisecond per division. Okay, and this is the drain trace. Let's see here. So that's the baseline for the pulse generator trace at 5 volts per division. The scope is calculating the duty cycle and the frequency. Looks like we're a little bit fast. Let me turn down that frequency just a little bit. Things are still warming up around here. Okay, so the frequency there is 2.396 kilohertz, and then checking that on the Phillips counter, 2.3985, 2.399, where is it? 399. So the scope and the master frequency counter are in very close agreement as to the frequency we're operating at, and we've managed to set that at 3.7% high, and that's the operating parameter for the Quantum 17 trials, right? Alright, there's the current waveform and the battery waveform. There's the zero for the battery, so you're seeing at 20 volts per division, you're seeing 24 volts on the battery. The current trace is displayed here at 200 millivolts per division. And the baseline, you can't see the blue dotted line, but the baseline is right down there. And the green dotted line is on the peaks. And the distance between those two cursors is 448 millivolts. Okay, and we have a duty cycle of 3.71%, right? Okay, so let's do the math here. Let's see, we have 0.448 divided by the current viewing resistor, which is 0.25, is 1.792 amps, times the duty cycle, which is 0.037, and that is equal to 66 millivolts, or 66 milliamps rather, right? 0.066. What does the meter say? 0.07. Okay, so hopefully that deals with the issue of the accuracy of these DMMs. I get the same value within very small error on the DMM as I do by taking the peaks, the duty cycle, and the CVR readings off the oscilloscope. Okay. Is that enough? And now here's the inverse of that prior duty cycle. Actually, almost the inverse. I could only get 95% high instead of 96.3%. I hope that's okay with you. 2.45. We're a little bit fast on the frequency. Let's have to adjust this big knob here to control that frequency precisely. 2.394. 2.394. That's pretty close to 2.4 kilohertz. Here's what the raw gate pulse looks like. There's the baseline. That's at 5 volts per division, so we're right at 10 volts. This is the drain trace. High is MOSFET off on the drain trace, right? Low is MOSFET on. This is what probably confused the early researchers. They see the drain trace going high for 4% of the duty cycle, and they think that means that the MOSFET is on, but it's not. The MOSFET is on when the drain trace is low. And let's see. After only 5 exposures, 5 or 6 exposures here, we're actually up to over 50 degrees C, and the ambient is about 25, so we're 25 over ambient already. And let's see, 23.7, 23.8 volts and 1.81 amps. So let's do the math again. Let's see here. The peak height of that trace is at 472 millivolts. Okay. And we are at a 94.9% duty cycle. So let's do the math. .472 divided by 0.25 equals 1.88 times 0.949 equals 1.79 against 1.81 indicated. Okay, so we're 20 milliamps out, 20 milliamps difference out of 180 or 1.81 amps. I'd say that was pretty good agreement. Wouldn't you?
Mm-hmm.